In the next part of the notes, we're going to discuss the common log. Now, we've talked about logs that have bases. For example, in part A, this one had a base of 5, this one had a base of 4, this one has a base of 64. The common base has a base of 10. So what that means is that it is written, and this is kind of goofy, it is written with nothing right there. So let's say we have log of 1,000. See how there's nothing written right there? It is an implied 10. Just like when you see an x, there's an implied 1 in front of it. This time, if there's no base written, it's an implied 10. Now if you look at your calculators, you can see there is a log button, and I think even like normal calculators have this, like even ones on your computer. And these normals, these are called the common log. It has a base of 10. If I could show you, it's going to be hard to see on this calculator. Can you see above the log? It's very hard to see, but can you see that it says 10 to the x power? That's because common log has a base of 10. Okay? Now take a look at your ln button. You should notice your ln has a base of e, but we'll get there later. Alright. So it's an implied 10, just like x has implied 1x. So it's just implied, just like x is an implied 1x. Many measurements of physical phenomena have a wide range of values that record measurements where logarithms or exponents of values, not the values themselves. When you use the logarithm of a quantity when you use the logarithm of a quantity instead of the quantity itself, you are using what they call a logarithmic scale. The Richter scale is a logarithmic scale. It gives logarithmic measurements of earthquake magnitude. Now that was a lot to take in. Here's what it pretty much says, okay? When you hear of an earthquake, on the Richter scale, of 5. Have you ever heard that? Like, oh, it was on the Richter scale, it would have been a 5, an earthquake, okay? That's not really 5 at all. What that implies is the Richter scale is a base of 30. So they're not just telling you that it was a 5 movement. They're telling you it was a 30 to the 5th movement. And this is talking about energy released. So the energy released is 30 to the 5th. 30 because that's the base of the Richter scale, and 5 because that's what the Richter scale would read. That's crazy. So when you hear of something going to a 6, okay? When you hear of something going from a 5 to a 6, you might not think that it's that big of a difference. But you'd be really wrong, because it's not just a 5 to a 6, guys. The energy that's released by that earthquake is from a 30 to a 5th power to a 30 to the 6th power. And if you could actually work those out, you would be amazed at how much energy is actually released, this versus this, okay? In other words, it would be 30 times as bad. So it's not just like, oh, it's an increase of 1. A Richter scale of 5 to 6 is 30 times as bad. Now, why would they never tell you 30 to the 5th and 30 to the 6th? Because those numbers are so big, they don't mean a lot. But now you understand, when you hear from a 5 to a 6, or even like a 5 to an 8, that's a huge increase of energy released by that earthquake. The following talks about how to graph logarithms. Now if you look, okay, let's do this. Logarithms are inverses of exponents. So the graphs are going to be very similar, but if I were to take a straight line like this, a straight diagonal, Do you see how they are mirror images of each other? This one up here is the logarithm. This one down here is, this one up here is the exponential. This one down here is the logarithm. Look how they are perfect inverses one of another. Problem 4, how to graph these. I'm going to go over very detailed steps on how to graph. Okay, this is what's the graph of y equals log 3 of base 3 of x, describe the domain and range, and identify the y-intercept and the asymptote. A lot is happening on there. Main idea is that y equals log base 3 of x is the inverse of y equals 3 to the x. So what we need to do is, which one of these do you know how to solve for? You know how to solve for this one. So step 1 is we're going to make an xy chart of 3 to the x power, because that's what we know how to do. So I'm going to pick -2, -1, 0, 1, and 2. I'm going to plug them in. 3 to the -2 power is 1 over 9. 3 to the -1 power is 1 over 3. 3 to the 0 power is 1. 3 to the first power is 3. I don't know why I put 9 down here. Can you please make that -2, -1, 0, 1, and 2? 3 squared is 9. Okay, now this is the inverse. We need, step 2, we need the log xy chart. Well, all I need to do is I need to take this one and I just need to find the inverse of it. Okay, so I do the one I know and then I switch it around here. So 1 over 9, -2. 1 over 3, -1. 1, 0. 3, 1, 9, 2. I'm not going to plot both of them. I'm only going to plot this one. So I'm going to go to my graph. Okay, but we should probably write this. We need the exponential equation to help make the log. Alright, now I'll graph this. Go over 1/9, down -2. Go over 1/3, down -1. Go over 1, up 0. Over 3, up 1. Over 9, up 2. Connect. Unlike square roots, logarithms continue down. Unlike square roots, logarithms continue down, so I'll draw an arrow on it. And now we have to talk about the domain. Look at the graph of our domain. I hope you agree the graph is domains, xy's, its x is greater than or equal to 0. And in fact, it will never be equal to 0 because it never actually touches this axis. The range is all real numbers because it goes forever up and forever down. The asymptote is, in this one, the y-axis, which if you needed a formula, that is x equals 0. Alright, moving on. We'll do the next one in another video.